Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture on basic control systems for mechanical engineers. In the first three lectures, we studied about linear systems, Laplace transform, transfer functions, and then we came to elements of control systems, and we also then focused on time domain specifications for controller design. Today we are going to study about a very important aspect of controller design, and that's understanding about stability. So here what we are going to do is understand when the system is stable, under what conditions, uh, some definitions about stability, and how to determine if a control system is stable. So our focus will be on LTI systems. An LTI system is stable if all the roots of the denominator polynomial which are also called poles, as we discussed in the preceding classes, have negative real part. That is basically all poles are in the left half plane. So what I mean by this is, say this is the S plane, this is the real part, this is the imaginary part, then the poles of the transfer function have negative real part, that is they lie in this region. So this region represents the stability region and is called the left half plane of this entire plane. And why that is so, we have seen in the previous class. So let us preceding classes, but let us just briefly go over that. So the real part being less than 0 implies that the response, if you see, will be something of this form. So this is, say, y of t, that is the output versus time, and here you see that it's decaying, this response, so it represents stability. Now this is the scenario in the LHP. If we are in the RHP, that is the real part of the pole is greater than 0, what you will see is the response looks something like this. So basically this is diverging, and this represents instability. So this is the definition of stability for an LTI system. In general, for any system, the stability can be defined using the concept of Bibo stability. So what does Bibo stability means? It means for every bounded input you should get a bounded output. For every bounded if for every bounded input we get a bounded output, then the system is stable. So mathematically this can be expressed, the input of any system can be expressed using the convolution integral in this form, where h represents the impulse response of the system, u is the input and y is the basically the output. Now let us start with bounded. If the input is bounded, that mathematically means basically that is less than or equal, the maximum value is less than or equal to some m which is less than infinity. So now if we take y, for the simplicity of notations we will draw this definition t. So basically the absolute value of the signal y is given by this. So we take on both sides, we take the mod. See, as you will see, this can be expressed, we can take the individual components now and we get this equation. Once we have this equation, we already know that u is bounded by m, so we can express this as m times negative infinity infinity h tau d tau. So now if we need our output to be bounded, then basically we need this integral to be bounded. So that implies that this integral is less than infinity. So this is the concept of Bibo stability, that is for every bounded input for that particular system we should get a bounded output, then that system is stable. So here we started with a bounded input u, maximum value of u is equal to m, and based on that we came to the conclusion that a system can be said to be Bibo stable if this condition is satisfied by its impulse response h. So this represents the concept of Bibo stability. Now let us take an example. So let us consider a simple electrical circuit here which consists of just one capacitance. So the capacitance is C, the current flowing is basically U, which is our input, and the voltage across the capacitance is the output Y. So the equation, dynamic equation for this system is ut is equal to C dyT by dt. That is, the current is capacitance times the derivative of voltage with respect to time. So we can convert this to the Laplace domain, which comes out to be of this form. So based on this we get h of s is basically y of s by u of s. So we can write 1 by Cs. Now the inverse Laplace transform of 1 by Cs is basically h of t is equal to 1 by C. So this is our h of t. Now we can take this particular integral which we have seen here with the condition for Bibo stability, and if you check this integral, what you will find that this is not bounded. So this implies that this system is not Bibo stable. So why one thing to understand about this system, it's a LTI system. With a pole on the imaginary axis right at the origin here in the S plane. So the reason this is not Bibo stable is because there is a pole on the imaginary axis. For Bibo stability of LTI systems, it is necessary that all poles lie in the left half plane. So that is the reason this system with a capacitor is not Bibo stable, because there is a pole on the imaginary axis. So far we have studied stability and then going into Bibo stability. Now let us look at certain concepts regarding stability. So let us consider y of s, and it can be expressed in the s in terms of transfer function, something of this form, a very general form where you have gain, zeros and poles. So we have m zeros and n poles, and m is less than or equal to n, that there are more poles than zeros, and this is necessary to ensure that the system still remains causal. Now once we have this, we can express y using what we call the partial fractions. So this can be expressed as some coefficient ki divided by si minus pi. So using this we can get the response, the inverse Laplace transform, like we have done in the previous lectures, as ki e to the power pit. Now this is assuming that all poles are real and distinct. Now this quantity e to the power pit tends to 0 if the real part of this particular pole is 0, is the real part is less than or equal to 0, that it is negative. Even if pi repeat, what we'll get as part of the response will be a get polynomial in T multiplied by e to the power pit, and we will get the same conclusion, that is we will get the system will still remain stable even if these pi are repeating, because we will just get a polynomial in t multiplied by e to the power pit. So, in terms of stability we get the same conclusion, that is the system will remain stable. Now, if these if pi are on the imaginary axis, then this system is neutrally stable. So, let us consider both. So, is neutrally stable and we get a oscillating output basically. Now, if pi are imaginary and repeating, then it is basically unstable. This is because what we will get is t e to the power plus or minus j omega t, and this t will keep on growing as time t tends to infinity, and that is the reason we will get, say something, if we plot this as a graph, this amplitude of this sine wave will keep growing and it will look something of this form, as compared to when we have just one pole where it's a sine sinusoidal wave with a constant amplitude. So, here we have three cases. The first one is if these if the poles are in the LHP, even if they are repeating, we still get a system to be stable. So, that is the first case. The second case is non-repeating poles on the imaginary axis result in a neutrally stable or marginally stable system. And finally, if there are repeating poles on imaginary axis, it is an unstable system. So far we have understood the concept of stability, and for an LTI stability what are the conditions. Now we are going to look at, say we are given a system, a closed loop system, as we had discussed in the previous lecture, is basically, say you have a system, a controller D, system G, and this is the reference, and say we assume there is unity feedback. In this case, the transfer function is dictated by this particular. So this we can represent the overall transfer function between y and r as gd divided by 1 plus gd. So for stability, what is the important part is this particular, the roots of 1 plus gd, that is basically this is we call the characteristic equation. So our next part will be understanding, say we are given this characteristic equation, under what is this characteristic equation going to be give us a stable system, and say we are given to design a particular control system D, we are given just in terms of gains, then under what conditions those gains can give us a stable system. So towards doing that, we will study what is called the Routh stability criterion. So the first thing is we need to determine, we will study the necessary condition. So say this 1 plus gd is equal to 0 gives, so 1 plus gd gives us a polynomial of the form a of s, which is s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 and so on till a n minus 1 s plus a n. Now the necessary condition is all coefficients of this polynomial should be positive. If all coefficients of this polynomial are positive, then we will get this characteristic equation will give us a corresponding stable system. Now coming to the sufficient condition for stability, a system is stable if and only if all elements of the first column of the Routh array are positive. So this is the sufficient condition for stability, that is we have to formulate the Routh array, and once we have formulated the Routh array, we have to check if all the elements of the first column of that Routh array are positive or not. So now we will understand how to formulate the Routh array. So what we will do, we will arrange these coefficients in the first two rows. So the first coefficient s power n is 1, then the next one is a1, then we will move up back to the first row a2, a3, a4, a5, and we continue in this manner till we reach an. Now these coefficients we can write b1, b2, b3. In a short while we will come to how to define b1, b2, b3. Similarly we can write c1, c2, c3. Now let us look at what is b1. So b1 is basically negative determinant. So we'll formulate a matrix. So for this, what we do here is we look for these B1, B2 and B3. The first column of this matrix will be basically this first column here. Now for B1, the second column will be the next column. So we'll get here 1, A1, A2, A3, and we'll divide this whole thing by the coefficient here, that is A1. So this will be basically A1, A2 minus A3 divided by A1. Now for the next one, if we want to find B1, what you will see is the first column of the matrix will be the same, that is 1 by A1, but the second column will now slide. So for B2 we look at A4 and A5, and the denominator division will be the same, we divide by A1. So based on this we get A1 A4 minus A5 divided by A1. In the same manner we can find coefficients B3 and so on. Now let us look at how to find C1. Now this will follow a similar concept. So it will now go to the previous two rows. So we will consider for all C1, C2, C3 and so on, we will consider this to be our first column of the corresponding matrix, and for C1 we will consider the second column here. So based on this we can say it is just negative determinant of A1, B1, A3, B2, and we will divide by the corresponding coefficient B1, the one just above the row C. Similarly for the next one, that is C2, the first column as we have seen will remain the same, whereas the second column will be will have to move to the next column. So we will get A1, B1, A5, B3 divided by B1, and in this fashion we will just keep on continuing till we reach to s to the power 0, and then we will have formulated an entire Routh array, and we look at the first column for the purpose of stability, and we will see what are what are the values of the coefficients. If all coefficients are positive, then it is stable. If there are some coefficients which are negative, we will look at the number of sign changes, which will tell us the number of sign changes will correspond to how many unstable poles there are in the system. Now we have done focused on the Routh stability criteria. We have seen the necessary condition, sufficient condition, and how to formulate a Routh array and check for stability. Now we will go into some examples about this. So the first example is, let us consider that this is our characteristic equation, s to the power 6 plus 4s to the power 5 plus 3s to the power 4 plus 2s cube plus s square plus 4s plus 4 is equal to 0. Now we are given this characteristic equation and we have to determine if the roots of this characteristic equation, that is the values of s we will get as the roots, have negative real coefficients or positive real coefficients, that is, are they in the LHP or RHP. So first thing we will check is the necessary condition. So if we check this polynomial, we will see that all coefficients are positive. So our necessary condition is satisfied. So we will now check for the sufficiency condition by formulating the Routh array. So let us start s to the power 6 s. So we will arrange the coefficients to be, and if you do not have any corresponding value, you set it to 0. So here we will take basically 4 into 3 minus 2, which gives us 10 divided by 4. So we get 5 by 2. The next one is 4 minus 4 divided, so this is equal to 0. Now we will consider next is this first column here and this fourth one. So 1 4 4 0. So 4, we get 4 into 4 divided by 4, so that is equal to 4. Next we now consider this particular portion here. So 4 5 by 2 2 0. So 5 by 2 into 2 minus 0 will give us 5 divided by 5 by 2. So that is basically 2. Next part we look as 4, 5 by 2, 4 and 4. So if we perform the calculation, this comes out to be minus 12 by 5 and so on 0. Now in this manner, if we go on calculating, we will get here 3, here 4. This is minus 76 by 15, 0 and 4. So here now we will look at the first column of this Routh stability array, and what you see is there is a sign change basically from 3 to minus 76 by 15, and again from minus 76 by 15 to 4 there is another sign change. So you see two sign changes which implies that there are two poles in the RHP. So this gives us that this system is unstable and how many poles there are in the RHP. That is the only information it gives us. It does not give us any more information about the location of the poles. So now let us look at another example. So we have s to the power 4 plus 2s cube plus 3s square plus 4s plus 5 is equal to 0. So if you check all the coefficients, then the coefficients are positive. So the necessary condition is satisfied. So we will now look into formulating the Routh stability array. So we can write 1, 2, 3, 4, 5 and 0. If you see this row corresponding to s to the power 3, it has a common divisor. So what we can do is we can instead write this s to the power 3 row can be written as 1, 2 and 0. So we have divided by 2. and then we can perform our calculations to get our route array. This is what the route array looks like. Now if we look at the first row, what you will see is this part here. So there are two sign changes, one going from 1 to -3 and then again -3 to 5. So this represents an unstable system. With two poles in the right half plane. So now we have studied the route stability array and we have considered couple of examples. Now let us consider another example. So let us consider the case where s to the power 5, 3s to the power 4 plus 2s cube plus 6s square plus 6s plus 9 is equal to 0. So all the coefficients are positive, so necessary condition is satisfied. We now move on to the sufficiency condition. So you can express this as 1, 3, 2, 6, 6, 9. As you will see, this has 3, 6, 9. So we can divide by 3. So we will get 1, 2 and 3. Now let us consider SQ. SQ, we will consider this part, the array will be 1, 1, 2, 2. So what we will get here is a 0. Next, when consider 1, 1, 6, 3, we will get 3 and this part will be 0. Now if we go on to calculate s square, what you will see is, okay, we will get the first part but the denominator will be divided by 0 and that becomes a problem. So this represents a special case which I will call this if the first term of a row is equal to 0. So in this case what we do is we formulate a new row. We, instead of 0, we assume that there is a small epsilon which is a small positive constant, and this epsilon is greater than 0 and basically so limit epsilon tends to 0. So it is very, very small. So based on this we can formulate a new row SQ where we have epsilon 3, 0. So based on this we can get S square as basically 2 epsilon minus 3 by basically two epsilon minus 3 divided by epsilon. Here we have 3 and 0. Similarly for the s to the power 1 term we have 3 minus 3 epsilon square divided by 2 epsilon minus 3, 0, 0, and when we have s to the power 0 term we have 3, 0. So now we will look for stability, we look at the first column. So to understand here, so let us first discard this particular portion here. So if we consider this epsilon, we have assumed to be a very small positive number. So this is represents, this is a small positive number. Then when we come to s to the part 2, the next part, that is 2 epsilon minus 3 by epsilon, this will basically represent 2 minus 3 by epsilon. So what you will see is this represents a with a very small epsilon, this 3 by epsilon will be a very large number, and since it's subtracted, this will represent a negative quantity. So this is less than 0. Next, if we come to 3, the next coefficient, what you will see here is this particular portion will be dominated more by epsilon in the numerator. So this will result in a small quantity, and this will, since it's 3 minus some small quantity, this will represent a positive quantity, and we have 3 is positive. So basically going from this represents basically a sign change here. So this represents 2 sign changes, because going from s to the power 3 to s square, there will be one sign change, and going from s square s to power 1 represents another sign change. So basically this system is unstable with 2 poles in RHP, and this is the way you deal if the first term of any row turns out to be equal to 0. Now let us consider another example where we have s to the power 5 plus 5s to the power 4 plus 11 s cube plus 23s square plus 28s plus 12 is equal to 0. So we can write down, we see all coefficients are positive, so necessary condition is satisfied. So we will get 1, 11, 28 here, here 5, 23, 12. Once we come to s cube, we start with 6.4, 25.6, 0, s square 3, 12, 0. Now we come to s, what you will find is for the entire row we get 0. So this is the case where the entire row is 0. So what do we do in this case? So in this case what we do is we go to the previous row and formulate, we consider, so this corresponds to s square, so we take 3s square, and then we go a couple of degrees below for s plus 12. So we get this particular expression, we take its derivative, we get 6s. So we formulate a new s as 6, 0, because we have 6s here, so we get this and we discard this part and we perform the calculations. In this manner. Now basically the implications of the entire row being 0 means there are poles which are on the imaginary axis, or basically there are a number of so there are poles on the imaginary axis and These poles on the imaginary axis can be basically the roots of this A1. So, we will simplify, we will get this 3s square plus 12. So, we get s square plus 4 is equal to 0, which implies that s is equal to plus or minus. So, that is the significance. When the entire row is 0, we have imaginary poles. Now, for the other poles, we look at the route stability array, the first column, and you will see all coefficients are positive. So, the other poles are perfectly in the LHP. So, there are no poles in the RHP, but there is a pair of imaginary poles. So far we have discussed the route stability array and a number of examples and some special cases. So, what we have done is, if you see all these 4 examples, what we have done, we have just checked whether a particular characteristic polynomial represents a stable system or not. Now, what we are going to do is, we are going to consider one example where we are going. So, for example, we are given a control system. So, our controller is just K, and a plant is given by s plus 1 divided by s into s minus 1 into s plus 6. So, this represents a closed loop system, and we want to find under what conditions on K we will get a stable system. So, to do that, we formulate the characteristic equation, which is 1 plus K s plus 1 into s minus 1 s plus 6 is equal to 0, and based on this we can get s cube plus 5 s square plus k minus 6 s plus k is equal to 0, which is our characteristic equation. So, what we do is we formulate the route stability array. So, we get 1 here, this is 5 k minus 6 divided, here we have k. So, we formulate we find S1 here. So, this is 5 and this is k. Now, what we do is we check if this particular is all positive or not, under what conditions it will be positive. So, basically 1 and here this 5 are positive. So, we will the condition is this 4k minus 30 by 5 should be greater than 0. Similarly, this last one k should be greater than 0. If we look at this condition, this turns out to be k should be greater than 7.5. And since if we consider both these conditions, this condition predominates. So, basically if k is greater than 7.5, this system is basically stable. Now, based on what we had discussed in the last class, let us consider this particular system. So, if you see, it has one unstable pole, but adding a controller, in this case just a constant gain k and unity negative feedback, what you will see is this system can be made stable by choosing k to be greater than 7.5. So, this implies that in a closed loop system we can we can stabilize even if the original plant is unstable. Adding a closed loop system, we can potentially stabilize the closed loop control system. Next, let us consider another example. So, we have a, a negative feedback, a plant 1 by s plus 1 into s plus 2, and we have a what is you'll see in later classes what we call a PI controller. So, this represents a proportional, and since it is divided by the second coefficient is divided by s, represents an integral controller. So, proportional integral controller. So, we can write the characteristic equation as so based on this we get s cube plus 3s square plus 2 plus k s plus ki is equal to 0. So, we can formulate the route stability array get 1 . So, now for stability, to ensure that this entire column is positive, we will get the condition that ki should be greater than 0, and then the other condition will be k should be greater than . So, if both these conditions are satisfied, then we will get a stable system. So, in today's class, we started out with definition of stability for an LTI system, understood the concept of Bibo stability, and then focused on cases where you have about neutral stability and what happens if there are poles on the imaginary axis. And then we went on to the route stability criteria. We first understood the necessary condition, that is all coefficients of this polynomial should be positive. Then we went to the sufficiency condition which focused on the route array. We defined the route array and then did a number of examples which included 2 special cases, and then focused on designing selecting the gains for stability for a P controller, in this case that is just proportional control, and a PI controller. In the next class we will focus about we will go more into depth about a PID, PI, and also the PID, that is includes the derivative term. So, for today that is all. Thank you.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfall. It should be a bullet point for people who are really interested to take up quantitative. So, consider the financial crisis in 2008 and later failing, different financial institutions are facing a problem like in Europe, in USA. So, the main thing is that even if you know the technique is best for people who are private players, organizations like banks, government, very somber manner such that the application area in the techniques which we learned can be utilized in the best possible way to the in-depth knowledge a person has in trying to utilize. And I am sure that people who have the background, who have the knowledge, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.